I'd like to go over how we're setting up our access road drainage. Not sure if you guys would like this kind of content, but if you would, give me a comment below. This is certainly a bit more technical than average, but just thought I'd throw it out there. I'm showing you how I design my own access road, so don't listen to a dude on the internet because that's the advice it's worth. So who's this presentation for? Anyone that's curious, obviously, but it's kind of a technical presentation and it's ensuring you have good drainage through a private access road. So any motivated landowner or an earthwork and excavation contractor who wants to be able to do better bids on their projects. And you should have basic algebra, like 8th grade math kind of skills. It's nothing crazy. I've set up most of the math for you so you can just kind of follow along. Context for this is we bought land. The driveway was steeper. We knew it was steep, but we didn't realize how steep until I started working on it. And when I went and measured it, it ranged between 16 and 21% grade. And that's just way too much for a northern climate that's gonna have lots of snow and ice. Our building site is up on top of a plateau, and it's about 170 feet above the county road. We're in the process of repositioning our road lower in the hill, and so we want to have it at just 10% grade all the way up. We'd love for it to be lower. I think the government specifies 7% as the maximum grade on a highway. That's not practical for us. It just ends up the driveway is way too long. It overshoots our house and gets into some really steep terrain that we don't want to have a driveway on. So you can follow us along and see how we build our driveway. This part, let's see how we design it. The topics I wanted to cover are the benefits to sitting down and doing the design on your road, what your road should be shaped like, then how to find what your soils are, your local rain, and how much runoff you have. Then we can find out how big your culverts need to be and how far apart they are, and then how to set up your drainage ditch so that we don't end up with any erosion. And I'll give you references to all of this in the description. So what is slope? It is the rise over the run. And so if you go forward 100 feet and up 10 feet, that's a 10% slope because it's 10 and 100. It's pretty easy to calculate. It's just the tangent of the angle is equal to the rise over the run. The best way to think about it is starting backwards. We can measure the angle really easily just by using a bubble app from your phone. You can just lay your phone down on the ground and it's going to say you have, say, 5 degrees. You need to turn that angle back into a slope. And so to do that, we just rearrange the tangent equation just a little bit, where we say that the slope is equal to the tangent of the angle. So a 5-degree slope, you take the tangent of 5 degrees and it's going to give you back your slope. Really easy to calculate. There's 3 basic types of road shapes that you can do for an access road. There's an outsloped road, and that's for very intermittent access. It's seasonal logging roads, things like this. You're not going to use that for anything that's a regular or permanent road. The next 2 are insloped and crown surface roads. Insloped is going to be typically a single lane road. It could be 2 lanes. Insloped roads are best used to be single lane, and the water sheds back across the road into a ditch and then is transported out further down the hill via culverts. And then a crown surface road does the same thing as an inslope, but it allows half of the water to go just right off to the outslope. Typically, you're only going to take the effort to make a crown surface road on a hill when there's 2 lanes. There's not much of a point for a single lane road to have a crown on it. The benefits of it is that water from the hillside never gets onto your driving surface, and so it dries a lot faster. The gravel on the roads is bound together by the fines, the dust, and that's what everyone complains about when you drive quickly down the gravel road. That's what really holds that road together, and by keeping as much water as we can off of it, we're helping keep the fines just bound up into the road. And a last and really important benefit for us is that vehicles sliding on ice will fall into the ditch rather than fall over the side of the hill. There's places where our hill can approach 45 degrees, and so it would be a really bad day if we went over that slope. One of the things I wanted to point out about the road shape for the inslope is that it needs to be between 3 and 5% inwards. And that's a lot. When you're on a paved road, the road slopes are only 1 to 2%. when you're getting out on gravel roads, they recommend 4%. And then if you can stomach it, getting up 5% is even better. And I think between, I might be misremembering it, but I think it's between 3 and 5%. So the two bounds, I think the amount of runoff silts was cut in half because the water got off the road much more quickly with the 5% than the 3. For finding your soil type, there's a couple different ways you can do it. The first, quickest, and easiest is to just feel that soil in your hand and estimate the soil type from there. There's the gardening way where you can put some soil in a jar with some water and shake it up, and you can kind of look at the different layers of sand, silt, and clay, and you can probably go find a video on that. Or you can use an online soils database. I've used the USDA Web Soil Survey, which absolutely works, but it's kind of clunky. It takes a while to get through it, and it's not exactly intuitive. You can also use Acre Value, which I believe is a paid app, but they do allow 2 free queries a month, or at least did when I signed up for it. We used that for our property, and it was really useful. It was quick and easy too, so that was nice. Our road is an ashy sandy loam and fine ashy sandy loam, and there's some clay in there too in various areas. Estimating the rain is probably one of the hardest things to do out of the whole bunch, particularly in the West Coast. The Southeast tends to have much better data. The Northwest does not have very much at all, and you're looking at a lot of plots and charts, oftentimes from the 1960s and 1970s, which, you know, they've got good data in them, but they can sometimes be really dense, or when they scan the document, it's really bad print. Where you're going to get that data from is NOAA ATLAS2. There's a reference down in the description for you. For our area, a 100-year, 1-hour rain event is about 1.4 inches, and I took and found where the 100-year 5-minute deluge would be, and the way that works is it's a percentage of the hour, and so for us it'd be 0.29, and so that means 1/3 roughly of the 1-hour rating is brought down in 5 minutes, and so you would take, for our 1.37 inches, multiply it by 0.29, and that's how much water comes down in 5 minutes. So then you'd scale it to get down to inches per minute. I keep everything in inches per hour up until the end, just because the numbers get too small, and so you start losing things in the decimals. But that's equivalent to almost 5 inches per hour. I think it's a conservative approach. I've never seen, when I was looking this up, people use the 5-minute data. Normally they're using the 1-hour data. Being up in the Northwest, it's not that big of a deal for us. If you're in the Southeast, you really want to look into that, because their 5-minute data could be just obscene compared to what it is for us. I've shown on this chart, there's a couple of, they're called Isopluvial charts, and so it's like a contour chart where each line is representing some amount of rain. And in the one shown, it's in tenths of an inch. So you'll see 18 gives us 1.8 inches. The chart below is that 5-minute duration, and it's got circle where we're pulling that data. One thing to note about that chart is that I believe it's calculating something down in southeastern Idaho. The data is conservative for where we are, and so we just went ahead and used it, so I didn't have to do all the math. Now that I have my rain data, we need to know how much actual water is falling on the ground on our driveway. We use the rational method, and essentially all that's doing is it's saying how much rain is falling as in inches per hour, and how much area do you have, and then what percentage of it stays, or what percent, as in soaks into the ground, and what percentage of it just runs off. The formula I've got on the screen, it's pretty simple. It's just Q, which is the flow rate, and that's going to be, I believe, gallons per second. Sorry, cubic feet per second. And then C is the runoff coefficients, I is the rainfall, and then A is just your area. So you take that and multiply it out, and that gives you your runoff. We do modify it because I've got the runoff rate for the road and the runoff rate for the hill, and they are different. In reference 5, I give you what the runoff coefficients are, and you can go find these runoff coefficients for all kinds of different soil types and different situations, so you don't have to just use what I've given you here. But for me, woodland sandy soils are between 0.1 and 0.3. Woodland clay and silt soils are 0.3 to 0.5, and then gravel was 0.5 to 0.6. Be careful though, because these numbers can be all over the place. I've seen some data sets, especially the FAO document, which I think is one of these references, it's really low. Whereas this one's more in the middle to high range. You want to be conservative so you're not undersizing your culverts. So then for our area, we have the width of the road, and then the uphill side of the road up to a crest. All that water has to come down. It's got to come down across the road. So you can take Google Maps and just guesstimate your from the edge of your road up to where the nearest crest is, or if there's something else that's going to divert the water, obviously only to that point. For us, it is between 90 and 150 feet wide. I'm just going to use 200 feet just so that I've got a nice even number to work with. Now that we have all that, we can go ahead and do the math to figure out how much rain do we get per 100 feet of driveway. And I like that just because it's a nice easy number to work with. So we take the area of the road, and I'm just going to call my road 12 feet wide. That's 100 feet long, so I have 1,200 square feet. And then I multiply that by that gravel coefficient, and so it ends up scaled down to effectively 720 square feet, and that's the square footage of the road that's causing runoff. The rest of it's absorbed. Then the area of the hill, we're just going to say is that 200 feet, and it's 100 feet long, so we have 20,000 square feet. We take that, multiply it by the 0.3, and now we only have 6,000 square feet of hill that's causing runoff. And we just go ahead and put all that together in the formula. You do have to be careful that, again, I was using inches per hour. That has to be divided out by 12, multiplied by 3,600, and that converts it from inches per hour to feet per second. And just be careful of your units there. At the end of the day, we get 0.74 cubic feet per second per 100 feet of driveway. And that's like 5.6 gallons per second. I mean, you think about it, that's a lot. That's a big 5 gallon jug. Just every second is coming through some point. Now we want to find out a little bit about culverts. This chart might look a little crazy. It's called a nomogram. And the way they work is you pick two of the three numbers and draw a line between them. And the line will then extend or cross over the third data point. And it's basically doing an algebraic equation for you. They're really easy to use once you understand them. Again, they look scary, but they're not hard to use. And you don't have to actually do anything with them. The data on this chart is what I pulled off for it. And if you wanted to use that, I think you'd be pretty close. So if we allow water to never go above the top of the inlet of each culvert, that's that first block of data, and that's a 12-inch culvert gives you 2.3 cubic feet a second. A 15-inch culvert gives you 4, and an 18 gives you 6. If we allow that water to go a foot above each culvert, the 12-inch culvert now gives you 4.7 cubic feet per second. The 15 gives you 7.5, and the 18 gives you 11 cubic feet per second. I'd like to use the 15 or 18 inch culverts just because, if you have silt buildup and you didn't get around to cleaning them as often as you should have, the functionality still stays there. And the other thing is that the larger culverts are a lot easier to clean than smaller culverts are, particularly if it's silted up. Now that you can see what the performance of each of these culverts are, and do keep in mind that that's a clean new culvert. If it's full of silt, it doesn't do nearly as well. But this now comes down to cost. A 12-inch culvert, just from my local supplier right now here in 2021, is going to cost me $260. The 15-inch culvert is going to cost me nearly $400, and the 18-inch culvert is going to cost me nearly $600. So while the bigger culverts are certainly nicer, that ends up being a lot more money. And so you've got to weigh that out, and where you have lower risk, maybe you want to go with a smaller culvert, and where you have more water or more collection, you probably should be safe and use the bigger culverts, even if you don't, on paper, necessarily need them. All right, now we need to figure out our drainage ditch. And this formula looks a little bit scarier than the last one. What it's trying to do is we're trying to find out how fast does the water flow through the ditch, and there's some numbers that I'll come up in a slide or two that tell us how fast water is allowed to flow before it starts eroding the ditch. The sketch I drew on the screen, which is from the FAO document, I think that was reference 1, is nice because it has a constant, what's called hydraulic radius, and that's just the area of the ditch divided by the wet perimeter. That's the little blue triangle I drew in there on the figure. So the formula is on the screen. I'm not going to go over it in great detail, but essentially the end result is we're trying to find out how fast is the water flowing. And this is going to tell us how far apart the culverts need to be. The figure in the bottom right shows the spacing between the culverts, and this is what we're trying to figure out right now. We can go and in the FAO document look up what the capability of various soil types are, so you can look in there, find your soils and see what it is. For us, alluvial silt non-colloidal is what was closest to ours, and if you think I knew what that was ahead of time, I didn't. That was go to Google and figure that one out. The non-colloidal portion is talking about how sticky is that soil, like what's the clay content. So we want to be under 2 feet per second, and that's going to keep the water from eroding our native soil. If we can't, we could put gravel down instead. And so gravel needs, and that's that bottom right number in the table, is 3.7 feet per second, and that's how fast the water can flow before it starts eroding gravel, basically carrying the gravel and the binders away. The Manning number, which was in that formula, is just another lookup. And for us, the very fine sand silt is 0.023, and gravel is actually about the same. I believe the Vmax is, in the right column there, is how fast can the water flow before that number is not really valid anymore. For you to be using those numbers, you need to stay under Vmax, and it's just something to keep in the back of your head. Okay, so from a few slides back, we had the rainfall rate, which is that 0.74 cubic feet per second for every 100 feet. I set up a simple Excel sheet, and it just calculates at various distances how fast the water becomes and when it's going to cause erosion. One thing I forgot to mention is that a number of the terms you need in that equation are actually in that figure up in the top right. It's the hydraulic radius, your area, and all that. So you just assemble the formulas together and put it in Excel, and then set up for, I did 100 foot, 200 foot, 300 foot. You can see at 100 feet, it's 2.87, which is too fast for our native soil, but it's not fully exceeded the speed of gravel. And then at 200 foot spans, it's a little bit over the gravel's capability. 300 foot spans is just beyond everybody. Because we're really conservative in all of our other assumptions, I'm going to go ahead and take that chance and set my spans at probably about 200 feet. Even though I'm a little bit above gravel's capability, I'm not so concerned that it's going to cause a whole lot of damage. This slide gives some notes on culvert installation so that you're following best practices. The culvert cross slope, and that's the road going across the road, should be 3% or more. That's considered self-cleaning. The culvert should be installed 30 to 45 degrees across the road. So if my hand was the road, you want the culvert angled at 30 to 45 degrees, so here or here, and obviously the water would be coming down, so it accelerates out and gets off onto the low side slope. If you're going to have a really deep fill on top of your culvert, you need to camber it where the culvert is sitting, like kind of like this in the middle. And over time, it's going to settle down to flat. If it's only like a foot, which is generally what's considered the best practice, you shouldn't have too much of an issue. And that actually leads to the next note: is you should have between 1 foot or half a diameter above the culvert to prevent collapse. And that's for like a big truck, say a concrete truck or a dump truck coming over. You don't want it to crush your culvert. Inlets and outlets need to be armored with riprap or gabion baskets, and that'll help prevent erosion. One of the things you can do on the inlet is if you put a rock that's jagged and pointed upwards. I mean, you probably need like 5 to 10 pound rock, but they're setting up like this. It's called dragon's teeth, and that rapidly decelerates the water. It'll cause silt to come out of the water, and so you're gonna have less likelihood of silt getting into the culvert itself. For your riprap on the outflow side, the water is going to be coming out at 4 to 5 feet per second based on those calcs we were doing, and it's going to be a little bit faster than the inlet, especially because now it's on a smooth surface. And just looking at this chart, which I think is also that reference one, it shows that you need 6 or 7 pound rock, which is about 5-inch diameter, to keep the rocks from being washed away as it comes out. If you're doing a cantilever culvert, it probably needs to be even more. Cantilever culverts are generally not preferred, but in our case, we're probably going to be forced to use them because you don't want the water to come out of the culvert and back undermine it. And so by getting it cantilevered out, we can drop it onto a gabion basket, and that'll help disperse the water and lower the energy. This is a list of references that we're using here, and I'll also have these in the description below for you. If you have any questions, comments, leave them down below. If I made a mistake or I didn't do anything right here, let me know. So people, I'll go ahead and pin those so that we don't end up with propagating bad data. Hopefully you guys like this, and thanks for watching.